What's up, guys? Um, I recorded a video yesterday, but it was only 50 minutes long, and I barely got through reading like this first paragraph here, so I was just so tired. But I woke up now, and I have a bit more energy in my system, so yeah, let's get this going. So we have to learn about forward and backward substitution, and the we know what LU decomposition is. So L is all these E's right here, and then U is the upper triangular matrix. But now we have to what is forward and back substitution? So let's say we have the LU decomposition of A, and we can access the entries of L and U. And we have the system AX equals B, and we'll have Y equals to U times X. So the forward substitution is a process of solving the lower triangular system Ly equals B from top to bottom. So y1 equals b1. This is row 2, column 1. Okay, solve the system ax equals b. Okay, we're just going to look at the example because this theorem doesn't, or definition doesn't really make sense straight out the gate. So solve the system ax equals b where a equals lu and b is this. Also, given an lu and a b, we can find an x, so we don't need a, it looks like. So we solve ly equals b. y1 is equal to -1. y2 is equal to okay, so solving ly equals b, so y1 equals b1. Y2 is equal to b2, so 1, minus row 2, column 1 of L row 2, column 1. Bruh. Yeah, it's row column, right? So row 2, column 1. Oh, and then minus, wait, row 2, column 1. Oh my god, it is 2 right here. is equal to 3, then y3. Okay, so it's sort of like a self-referencing kind of. Now then we solve ux equals 3, so yn over un comma n. So we got y3, no, so x3 is gonna equal to y3, which is 0. Okay, so at y2, x2 is gonna equal to y2, which is 3 over, well, y2 is 3 minus u2 u2 3. So row 2, column 3. Divided by un minus 1, so u2 row u of your column, row 2, column 2, which is 1, so it's also 3, and then x1 is equal to, okay, I think I'm starting to understand now. So this is how we arrive at a solution for x. Okay, I understand it now. That's loud. Paste this definition in real quick. Awesome. Okay, we're almost through the first section of this course. Oh my. I know during the summer course you're gonna go through one section every day, and I hope with my limited attention span I'll be able to keep up. So note, the LU decomposition is especially useful when solving many different systems with the same coefficient matrix A. Wait, when is LU decomposition useful? Okay, so there's a time complexity aspect. Mm, There's a lot of problems. Do I want to do these exercises first, or do I want to do this first? Okay, let A be an m by n matrix, so m rows and columns, n rows, m rows and n columns. Determine whether the statement is true or false. If the number of rows is bigger than the number of columns and the rank of A is n, then there's a unique solution if you have more columns than rows, then we can't possibly have a unique solution. I think this has to be false, right? Oh wait, it says the number of rows is bigger than the number of columns. Nah, I think it's still false. I think B is true. So A is false, B is true. If the rows is bigger than columns and the rank is equal to columns. Wait, what the heck? I think it's false, true, false. Then if the system AX equals B has one solution, then there are only one solution. Oh. If M is bigger than N, I think false. False. Okay, we got A right, B right, C wrong. D wrong. But we got A, B, C, D, E right. If A is invertible, how do we when A if the A is a square matrix whose diagonal entries are all non-zero, then A is invertible. How am I supposed to? I don't. I wish there was like a. Wait. You know what? I don't want to concern ourselves too much with the problems right now because I do want to code. Okay, let's code this decomposition stuff up. A dot shape np dot I. Let's. Okay, let's see what's going on here. Alright, I'm gonna try to make a second video today to make up for yesterday. But yeah, I'll see you guys. We understand forward and back substitution now, and we're beginning to understand how the LU decomposition function works. So little steps forward.